Assalamu alaikum wa rahmatullahi wa barakatuhu. In this particular course on electrical machine, we will see what is an electrical machine and how an electrical machine can be used to transform a mechanical form of energy into an electrical form of energy and vice versa. So, in this particular course, we will also study the transformers. Now, the first question here is that what is actually an electrical machine? An electrical machine is actually an apparatus which is used to convert mechanical power or mechanical energy into an electrical energy and vice versa. So, an electrical machine, if it converts this electrical form into a mechanical form, we call it a motor, and if it converts the mechanical form into an electrical form, we call it a generator. Notice here that this conversion requires to have an action of magnetic field that interact with the mechanical part and the electrical part. So, there is a magnetic field requirement here which is used to convert this mechanical form into an electrical form or from the electrical form to the mechanical form. And we have so much practical usage when it comes to the electrical machines. Now, notice here that when we say that we have a conversion of mechanical power into electrical power and vice versa, the transformers do not come in an action. So, where do the transformers fit in this particular course? You see, although a transformer is a static device without having any moving parts, the input port is electrical, the output port is electrical. However, this transformer interact such that the voltage transformation from this primary side to the secondary side depends entirely on this magnetic field, and therefore alongside the pure electrical machinery, we also study the transformer in this particular course. We will try to stick entirely to the SI units. However, sometimes we may use the English units as well, for example, inch, feet, pounds, etc. Also, we would like to write all the phasors in this particular type of a font. However, if it is not like this, I will verbally explain that if it is a phasor quantity or a time varying signal. This machine course requires to have a basic understanding of the magnetic concepts, because everything in this whole process depends on this magnetic field. So, there are 4 principles of the magnetic field. The number one is that if we have a conductor something like this one, and there is some current that flows into this particular conductor I, then we have a magnetic field around this particular conductor, and this magnetic field direction we can find it out by using the right hand rule, right? So, this I, if it is your thumb, if it is pointing the direction of the current, then the rest of the fingers, if they move into the into the wrist side, then this is the direction of the flux or the magnetic field which is developed in this current carrying conductor. So, the first important point in understanding the role of magnetic is that any current carrying conductor produce a magnetic field around it, right? And this magnetic field strength, this particular thing, that how far we have this magnetic effect of this magnetic field is, it depends entirely on the amount of current that flows through this particular conductor. So higher this value of I, higher the value of I, more is the magnetic field. This is the first point with respect to the electrical machine course. The second point is that a time varying, right, a time varying magnetic field induces a voltage in a coil of wire if it passes through that coil. The third important point here is that a current carrying wire in the presence of a magnetic field will experience a force induced on it. And the final, or the fourth basic principle of magnetic field with respect to the electrical machines is that a moving conductor or a moving wire in the presence of magnetic field has voltage induced in it. Now, if we closely examine these three, this particular part, number 2, it is related to the transformer that we study in this particular course as well. This part 3, which states that a current carrying wire in the presence of magnetic field experience a force induced in it, actually is a motoring operation or a motor action. Whereas this last part, that a moving wire in the presence of a magnetic field has voltage induced in it, it represents, or it is pertinent with the generator, action, right? In electrical machines, we only study 3 things. So electrical machine, or the understanding of electrical machine, requires, number 1, the construction of the machine, number 2, principle of operation, and number 3 is linear circuit analysis. As far as this particular course is concerned, understanding of these 3, understanding of electrical machine is dependent on these 3 points. So we will see the construction of machine, then the principle of operation, and lastly we will use linear circuit analysis to understand the electrical models of these particular machines. So let us move ahead and see how a magnetic field is produced. So the production of magnetic field. The starting point of understanding that how a magnetic field is produced is the Ampere's law. Ampere's law states that the magnetic field H dot dl is equal to the I net or the current enclosed. Where this H, it represents the magnetic field intensity, and this dl is actually a small element of length L. Now, to understand how this Ampere's law actually works, let us draw. So, we have this particular core. In this particular core, let us say that we have some wires wrapped over it, something like this one. And because we have applied some voltage here, there is a current which is flowing into this particular winding. Let us say that this particular winding has n number of turns. So, we have 1, 2, 3, 4, 5, 6. So, instead of writing 6, let us say that we have n number of turns that are wound on this core. And this core is actually made up of a ferromagnetic material. And we also consider that this ferromagnetic material is actually a lossless material, right? Which means that the field is not leaked or it is not lost in this particular core. And this LC, whenever we have this current flowing here, then we will see that there is a flux that will produce in this particular core. Let us say this is phi. Now, if you can see that this core flux shall have a mean length, because it will be present in all the different parts of the core, here as well, and also inside in here as well. So, we say that instead of making the things complex, to make the things simple, let us say that this flux which is generated in this particular direction based on the right hand rule, we say that this mean length of this flux is this LC. So, I say that LC is the mean length of the flux path, right? So, the total current that is enclosed here is I net equals to N into I, where N is the number of turn and I is this current. Why I am saying this? Because the current will only flow in the area where we have these N number of turns wrapped in this particular coil. This means that the coil of wire, the coil of this particular winding will cut the path of this flux N times while carrying the current I. So, the Ampere law can be rewritten as HLC is equal to N into I, where this LC, as I have said, it represents the length, mean length of the flux path within the core. And based on this, I can say that this is H, that is equal to Ni over LC, right? And this unit is in ampere turns per meter. This means that the magnetic field intensity is actually proportional to the number of turns of the winding as well as the current which is flowing in these particular coils. We can also see here that this magnetic field intensity, which is this H, magnetic field intensity H, is inversely proportional to the length of the flux. So the magnetic field intensity decreases as we have this mean path length of the flux increases. If it increases, then that actually decreases. So because of this magnetic field intensity H, we do know that the magnetic field density B is equal to mu into H, right? So this B is the magnetic field density. This is magnetic field density. That is the flux lines per unit area. That is how much of this flux is actually passing through this particular area. That represents the magnetic field density, and that is equal to mu into H. H is the intensity, B is the density, and what is mu? Mu is known as the permeability of the core material. This discussion actually states that the magnetic flux density B in any piece of core is because of the current that establishes the magnetic field, and thereafter that magnetic field actually exerts the force or the effort to develop this magnetic field density, and therefore that is known as H. Now the question here is, for a given material, how easy or how feasible or how convenient it is to produce a magnetic field in a given material, that is judged by a particular terminology that is known as permeability, right? So the unit of this permeability is Henry per meter, and this H we have already written as ampere turns per meter. So the unit of this magnetic field density equals to Henry ampere turns per meter square, and that is equal to Weber per meter square, or in other words, it is also known as Tesla. Now this mu is a very important phenomena in choosing the core of any electrical machine, because the electrical machine requires to have a magnetic field in the core so that the input port and the output port can interact without having a physical connection between them. So we always judge the material by something that is known as the relative permeability, and this concept is similar to the concept of the altitude measurement, which is with respect to the sea level. So when we say that a particular place is 5,000 feet above the sea level, it shows its altitude with respect to the sea level. So whenever we design an electrical machine, the requirement of selecting some core with high permeability, we refer it with respect to a reference value, which is the permeability of free space. And you might have seen this in your earlier physics course, that this mu naught is equal to 4 pi into 10 raised to the power minus 7 Henry per meter. So this is our base value now, and based on this we measure the relative permeability equals to the permeability of a given material divided by the permeability of the free space. This gives us the relative permeability. Now how can we interpret for a given relative permeability about a given material? For example, I say that for steel, I say that this mu r is equal to, let us say it is 3000, right? This 3000 should ring bell in your mind that for a given amount of current, this steel with this relative permeability of 3000 will produce 3000 times more flux. Steel produce 3000 times more flux compared to the free space or air. And remember that for this, we assume that we have same corresponding area, right? So we have the same corresponding area for the steel, and then for the same area in free space, the steel shall have 3000 times more flux for the same amount of current. So this concept of relative permeability, this is the relative permeability. This concept of relative permeability is very important and a very essential ingredient, particularly in machine design and generally in understanding the behavior of and the importance of the core or the magnetic carrier, which is over which the magnetic field is generated. It is a very important part. So the materials used in a transformer or motor core play an important part in increasing or concentrating the magnetic flux within that device. And generally speaking, we require to have, for a good design we have high permeability, so that less amount of current is required to establish a given flux, right? And also that the majority of the flux remains inside the core, because in a practical way, not all the flux will be produced inside this core, because we have said that it's a lossless material. This ferromagnetic material is not available such that we do have losses in a practical system. So some of the flux actually leaves this particular core, right? And this particular flux that leaves the core is known as the leakage flux. We will discuss this in some next class. So in the figure that we have shown here, mu B is equal to mu H, and what is mu? Mu is the Henry per meter, and H is equal to number of turns into current divided by this LC. So if I substitute the value of this H into this B, I get NI LC into mu. And in order to find out the total flux in a given area, we have to integrate that. For that, we can say that the total flux in a given area is equal to area, and we divide and we integrate this at B dot dA. So this phi is equal to BA, that is equal to mu and I over LC into this A, where A is the cross-sectional area of the core. Cross-sectional area, core cross-sectional area, right? Now that we have seen that this flux is equal to mu and I LC over LC into A, it actually means that to produce this flux phi, there must be some current in the coil of a wire which is wrapped around a core. because this mu is dependent on the material and represents the number of turns. A is the area, LC is the mean length path of this flux. So I is the force which produces this particular flux. Next is the Faraday's law. Faraday's law states that the rate of change of the flux is proportional to the induced EMF. The more we have the rate of change of flux, more is the induced EMF. So E induced is equal to d phi over dt, although there is a negative sign associated here as well, which is because of this Lenz's law, and which states that the direction of the induced EMF is such that it produces the cause that is actually generating it, right? So the induced voltage opposes the change that causes it. And that is why we require to have this negative sign here. Also, we have seen that if we have a coil with n number of turns, then the induced EMF is then equal to minus n d phi over dt. However, the resulting voltage, whatever is produced, we can establish the polarity by physical consideration, and therefore we usually do not write this negative sign with this E induced. And therefore, throughout this particular course, we will only use E induced equal to n d phi over dt. We will not be using this negative sign. Now, this particular equation has some assumptions. The first assumption is that we have no leakage of flux from the core, which is not practically possible. However, there are certain practical measures that the designer should take in order to minimize this leakage. So the damage control is there, but this cannot be avoided 100% because we do not have a magnetic material which is 100% ideal. The second thing is the phenomena of the eddy current losses. So if I go back to this particular diagram, we can see that in this particular diagram, if this core is made up of a single material, then this flux is also interacting with this core material. And with this interaction, what happened that we have localized currents or the induced, because of the induced voltage within the core. And this localized current actually have this type of a shape. They represents or they looks like the eddy currents that you might have seen near the shores of the river and the sea. But this eddy current, what these eddy currents are, these are localized current, right? Localized currents mean that they do not have the entire path, rather they will produce here, some will be here, some will be here, etc. and etc. So what happened here, that the production of eddy current, produce losses. Why we have losses here? Because we do have some resistance in the core, and because there is a current flowing here, so the power loss is equal to I square into R core, where R core is the resistance of core material. So how can we actually reduce these eddy currents? Because when we have this constant I square R losses within the core, then the core actually produce heat. So how can we reduce the eddy current losses? Eddy current losses can be reduced by two means. Number one, we use, instead of having instead of having a single piece of core, we use laminated sheets, and then we join them together with lamination so that the localized current circuit can be reduced, right? So with this laminated stack of sheets, or we have strips of core combined together through lamination, right? And that lamination is actually an insulating material. So using this thing, it divides the area of the current, eddy current, right? The eddy current, and hence it reduces the losses. The second point is that instead of having these multiple strips, we add resistance to the core material, and this is usually done by adding material like silicon, right? But for effective way, both this one and this two are used to reduce the eddy currents, right? So far we have enough of the information which is required to start the topic of transformer. Regarding these point number 3 and point number 4, we will revisit them when we will start the topics of the electrical machines. So let us start the topic of the transformers. Transformer is a static device. The number first property is it's a static device. What it do? It shifts the voltage level applied on the input port. For special case, it may not shift the voltage applied on the input port, and that particular usage of transformer is only for electrical isolation. But for a general rule, it has to shift. It is a device, static device. That means we do not have any moving part. No moving part here, and it shifts the voltage level applied on the input port while keeping the frequency and power same. What does this mean? This means that if we have V1 greater than this V2, then we have I1 less than this I2. That means that the input power P in is always equal to the power on the secondary side or on the output side, P naught. Okay, so transformer has its construction. It has only two parts. Number one is the core, and the other one is the winding. So as far as as a basic transformer concept is concerned, we have a core and then we have a winding. We have earlier discussed that for the core material, the core is made up of laminated sheets. But the core shape also plays an important role in deciding the cost associated with the core design and the winding. So core is further of two types. One is known as the core type transformer and the other one is known as the shell type transformer. The core type transformer has this type of a shape where we have these one, there we have the laminated stack of sheets available, right? And over them we wind the primary winding in here, while the secondary winding is wrapped here. So this is a primary side, this is primary winding. Primary winding is also the input port, and the secondary winding is usually the output port. Some transformers may have more than two windings, right, that are specifically used in power electronics, where we have multiple outputs. For multiple outputs we require to have one primary and multiple secondary windings. But for the time being, just consider that we have one winding for the input and one winding to connect the load, and therefore this primary winding and the secondary winding are shown here. So you can see here that the magnetic path that will appear here within this particular core, consider here, it actually forms a small ring which is encompassed by a group of primary and secondary windings. Now this core type transformer has some issues. What is the issue here? The issue here is that we do not have a flux linkage here. Nor we have here. So we address this problem by using a more expensive form of a transformer core, which is known as a shell type core. Here we have the primary winding, right, and over that we connect this, or we wrap the secondary winding. Again, the common point here is that for both the transformers we have a laminated sheets to reduce the eddy currents in a given core. What is the advantage here? You can see that we have the windings one over another. Which means that we have better flux linkage, not only because both of the windings are wrapped over each other, but because these windings are encompassed by the material of the core, which is shown here. So you can see that the primary and secondary winding from this middle limb are encircled or engulfed by two or more rings of magnetic material, which is here, right? So that is why we have a better flux linkage here. Now the question arises here that for some transformer, let us say, where we have the primary voltage Vp greater than this Vs, which winding will be wrapped on this limb and which winding will come over it? It is a simple rule that we wrap the high voltage winding over the low voltage winding, because it addresses the insulation problem to avoid or reduce the the insulation problem. Now, as far as this particular core is concerned, this core type, we know that this looks like we do not have much material required to create a core, and hence it is a cheaper solution compared to this expensive solution of a shell type transformer. But because we want to enhance the performance of this particular core type core of a transformer, we have some tricks here. The trick is that, say we have this we have this transformer. Now, instead of having the entire primary winding linked on this side, we wrap the half of the primary winding on this limb and half of the primary winding on this limb, so that we can somehow create a better flux linkage between the primary side and the secondary side. So this can be done by actually having half of the primary here, right, and half of the primary in here, and then we can take it here. So this is the V primary. About the secondary, we have the secondary here that is taken outside from this side. So this is Vs. So with this particular arrangement, you can see that now the primary winding and secondary winding both are wrapped on both of the limbs of this particular core, and therefore the problem of weak flux linkage is somehow addressed in this configuration of the winding. This is known as interleaved winding. And this is a usual thing that is adopted in industry. And in some textbooks, it is shown something like this one. We have it here, and then we have it here. Something like this one. So we can see that we have, in some textbooks, it is shown here. Right, though this is Vs and this is Vp. So having said that, we have two types of cores. We have established that with the physical inspection, we can see that the core type is a much cost-effective solution compared to this shell type core. We can also see that we have a high leakage in a core type compared to a shell type core. But this can be compensated a little bit by using a technique where we interleave the primary winding and the secondary winding. Now, before we move ahead, transformers are not only classified, let us say, classification of a transformer. So transformer can be classified in terms of, number one, the number of phases. We have single phase and we have three phase transformers, and we may have some special design where we can cater more than three phases. Then we have a classification of transformer with respect to the output voltage. So here we have step up transformer. Here we have the step down transformer, and we also have a unity transformer which is used for electrical isolation, because this electrically there is no connection between these two wires. They are enameled wire, they have the insulation, so they are not passing any current into the coil, into the core of a transformer. So this is the second classification of a transformer. Other than that, we may have a classification with respect to the windings. So we may have a center tap transformer, we may have single input, multiple output windings, and so on. We can also have a classification of the transformer with respect to the application in power systems. For example, we may have a transformer known as a unit transformer, which is connected right after the generator, and it lifts up the generator voltage to the transmission line voltage. Also we can have a substation transformer. This substation transformer is actually used to step down the transmission line voltage, which may be of 500 kV, 132 kV, 66 kV, depending on the national grid. It stepped down the transmission line voltage to the distribution level voltage. Then we have the distribution transformer, which is commonly you can see in your colonies or the residential areas where you live. This distribution transformer is again a step down transformer, and it step down the distribution level. For example, in Pakistan, mostly this is 11 kV to the domestic level or the domestic device level, which is 220 volt RMS in Pakistan for single phase and 380 for three phase. We also have the transformer which is known as an instrument transformer. What is this instrument transformer? You see, we have very high voltage on the transmission lines, which cannot be measured through any other practical device. Something around 500 kilovolt, it's insane to measure it through any of the handheld device that we have. So instrument transformers are special type of transformers which are used to measure high voltage and current, particularly in a transmission line. So it has two types. One which measures the high voltage, we call it potential transformer or PT. PT is the famous name here. It used to measure the voltage. And also we have the current transformer, which is known as CT, and as its name implies, it is used to measure the current flowing in a high power network. So having said that, let us move ahead with the concept of the ideal transformer. When we say that we have an ideal transformer, it means that we have no losses. We have no losses in a given transformer, and that losses mean we neither have the electrical losses and nor we have the magnetic losses. So the electrical losses account for the winding resistance. So the winding resistance is 0, and the magnetic losses pertains with the core, which never saturates. We will discuss the other parts in another upcoming video. So in ideal transformer, it is not feasible to design these cores every time we design a transformer. So we have an elementary model of a transformer that will be widely used throughout this course. That is, we will only use this type of a shape, and we will connect some winding here. So we have a current which enters here with this applied voltage VPT on the winding which is known as the NP, where N is the number of turns on the primary side. And in here we have the current direction, something like this one. Also we have on the secondary side, we have the voltage in this particular polarity, as well as the current leaving this particular side. So in a practical transformer, it is not at all feasible to see which point is positive with respect to the other point. So we use a term which is known as this dot convention. It is a very feasible way of establishing that which end is positive with respect to the other end. So the dot polarity, let me write it here, dot polarity, it has two important points. Number one, the dot ends on both of the sides, whether this NP or NS, the dot ends are, the dot ends have same polarity with respect to the non-dotted ends. So if I have a positive here, then I have a positive here. If this dot end is negative with respect to this non-dot end, this is the non-dot end of the primary side, and this is the non-dot end of the secondary side. Then both the dot ends with respect to the non-dot ends of their respective sides shall have the same polarity as we have shown in here. The second point is that the current enters the input port dot end and leaves the output port dot end, which means that if we have the current flowing into this particular dot of this NP, then the current shall leave from the dot end of the winding NS, right? So in an ideal transformer, using this dot end, we have established this particular elementary model of a transformer, and that is used to analyze the ideal transformer as well as the real transformer. So in this particular elementary model, we have the P input equals to the output power. So we have VPT over VST, and that is equal to NP over NS, and that is equal to A, where is the ratio of the primary side number of turns to the secondary side. And also we have this number of turns on this side, we have a balance here as well. So therefore we have IPT over IST, that is equal to 1 over A. And in terms of the phasors, this VP over this VS is equal to IS over IP, and that is equal to A, where A is equal to NP over NS. What does this mean? This means that if we have, for instance, you can see we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let us have another winding in here, so that now the number of turns on the primary side is greater than the number of turns on the secondary side. Then if there is a load connected, then the current in the primary side and in the secondary side interact in an opposite way as compared to the voltage available on the secondary port, secondary side and in the primary side. So this turn ratio A, which is equal to NP over NS, is used to decide whether a transformer acts as a step up transformer or as a step down transformer. And this transformer, an ideal transformer, it has no impact on the phase angles, which means that if we have this is the primary voltage, this is the primary voltage, then let us say we have a step down operation, then this primary and secondary voltages are of the same phase, right? And so is the current. Also, this particular model is good for analysis, but in electrical diagrams we do not use this model. In all the electrical circuit diagram, we use another type of a model that is known as this particular model, right? So in here you can see we will again write this. This is VPT, this is VST. Here we write the dot ends. Here this is IPT and this is IST, and we say this is NP ratio NS. And if we have these two parallel lines in between them, it represents that we have an iron core in here, right? The core is there. Otherwise, it may be an air core transformer. So the power associated in a transformer, as we have said, that this P in is equal to P out, it means that the input power, the real input power is Vp Ip into cosine theta P, where these are the phasor quantities, and so P naught is equal to Vs Is cosine theta S, right? And in an ideal transformer, as I have said here, that we have this theta P is equal to theta S is equal to theta, so there is no impact on the phase angles through an ideal transformer. Similarly, we can see that the same relation actually exists for the reactive power as well. So Q in is equal to Vp Ip sine theta P, that is equal to Vs Is sine theta S, and that is equal to Q out, because this theta is equal to theta P, theta S is equal to this theta. And similarly, the apparent power S in is equal to Vp Ip, and that is equal to Vs into Is, and that is equal to S out. Now, other than this particular concept of the powers, the impedance transformation through a transformer is also a very important concept. So let us wrap up the particular lecture on this impedance transformation. Impedance transformation through a transformer. Suppose that we have a transformer here and we have some load with impedance ZL here. Now we have some current IP and we have some current IS here. So we have the voltage applied, V voltage here, and here we have the secondary voltage across this secondary winding. This is NP and this is NS. Suppose that I want to see how this impedance ZL, which is the load impedance, it is related to the impedance on the primary side, which I will call it ZL dash, right? So I need to see this thing. Now if we apply the basic circuit analysis here, this ZL dash is equal to Vp over Ip, right? And since we know from these particular expressions, Vp and Vs are related through the turns ratio A, and so is this Is and Ip as well. So I can say that this Vp is equal to A times Vs, and this Ip is equal to Is over A. So this ZL dash is equal to A times Vs divided by Is over A, and that is equal to A square Vs over Is. Now we also know that this ZL is equal to Vs over Is. So, this ZL dash is equal to A square into ZL, right. So, for example, if we want to match the impedance of two devices, we can use a transformer. And therefore, and by experience, I am telling you that this transformer based impedance matching is very popular in amplifier based sonar systems. So, we connect a transformer here, and here we have the have this particular type of, let us say we have a sonar system or an amplifier here, right, or a speaker here. So, we have some impedance of this amplifier, we have this Z dash, and this sonar or a speaker, every speaker has its own impedance, that is known as ZL. So, if we want to maximize the power or maximum power transfer theorem, we want to implement it on it, we need to adjust the turns ratio here with this A square, where A is what? It is NP over NS. So, we can actually match the impedance of a particular source and a load through a transformer. This particular expression also says that we can shift one side of a transformer to the other side, and this process is known as the referring process. We call it a referring process, right. So, what is it is we shift one side of a transformer to other side. So, for example, in this particular side we shifted the secondary, referred it to the primary, and that is why we have this ZL dash equal to A square into ZL. So, if I want to shift this ZL onto this primary side, I have to multiply it by A square, and this process is known as the referring the secondary to the primary side. If I take some impedance from this primary side to the secondary side, then that process is known as referring the primary side to the secondary side. With this in mind, so let us end this particular lecture. In the next lecture, we will discuss the theory and operation of a real single phase transformer, where we will see that the transformer with losses requires to have some important some important factors in order to understand the operation of a real single phase transformer. So, till then, I thank you all and take care, and Allah Hafiz.